Hello folks, we're back. We are at section 2.34 talking about maximum likelihood for the Gaussian. So what does that mean? The idea is that we've got n points, n observations, which are drawn independently, so that's the key thing. We're assuming that they've been drawn independently from a multivariate Gaussian distribution, and we're interested in estimating the parameters of that distribution. And so we're going to do that with maximum likelihood. So the idea is that we're going to have a likelihood function, a log likelihood, and we're going to maximize it with respect to mu, which is the mean of this multivariate Gaussian, and sigma, which is the covariance. Now, in this section, what he does is he essentially just states the results. So we're going to state the results of that maximization. But I think the techniques and they're kind of quite simple techniques, and they're just differentiating, essential techniques are differentiating functions of vectors and matrices. I think those are quite useful. I find them very useful. I use them all the time. And so what I thought I'll do is, in this particular video, I will just state the results that we're going to encounter in this section, which is all that's there. But in the next video, I'll show you how you can actually derive those results yourself. And that's really useful. It's something that I think you should just really learn and become really comfortable with, because it'll just come up all the time. It'll make your life easier. You're very often going to get situations where you have functions, not necessarily log likelihoods, but functions of vectors and matrices, and I mean scalar functions. So functions where you have a matrix and it's mapping to a single value, and you want to differentiate that function with respect to the matrix. You can always go through it and do it element by element, but I quickly learned that if you actually learn the very simple tricks for how to just differentiate with respect to the matrix, your life becomes so much easier. So what I want to do is, in the next video, I'll essentially show you how to do that, focusing on this particular function that we care about here. So you'll see all the details of that, so you can learn that and use that in your own work. And in this particular video, we'll just kind of state the results that he's going to state in this section. So think of this as kind of part one of a two-part video. Okay, so let's get going with that. Okay, so the very first thing is that the log likelihood function. So he says the log likelihood function is given by this. Where does this come from? Okay, so this is just quite simple. Let's just kind of work it out. So the idea is that if we have a single observation, you'll remember that for a single observation, the probability of x, so this is going to be the likelihood of the parameters for that single observation, is going to be equal to, so it's 1 over 2 pi to the d over 2 times the determinant, the square root of the determinant. And then, of course, there's the all-important term in the exponential. Okay, so that's going to be x minus mu times the precision, x minus mu, and mu is the mean that stuff is coming from. Okay, so the idea here is that now we're going to do we can maximize. This is just for a single observation. So now what happens for n independent observations? So the idea is that now so now that we've got this, now then for the probability of x, which is now going to be this full set of observations, given mu and sigma, this is going to equal to the product. So this is where the independence comes in, xi given mu and sigma. Right, and actually let's just to make it even more similar to what he's written, let's make it xn given mu and sigma, and n is going to equal to 1 to n. So you just multiply all of those, and now if you then take the logarithm, so now we're getting close to what we're actually going to be differentiating. Well, that's just going to be equal to the sum. So this product becomes the sum of log p of xn given mu of sigma. Okay, and so now if we then just take the logarithms, then you will see that, okay, so if we actually take the logs, for example, this term up here, well, what's the log? So that's going to be minus d over 2 log ln. When I write log, just read ln, natural logarithm, 2 pi. But there's going to be n of them, right? Because we're doing this summation over the n terms. So this is actually going to become an n times d over 2. And then there's going to be a second contribution that's going to be coming from the square root of the covariance, of the determinant of the covariance. So one of those is going to contribute a minus log minus 1/2 because of the square root log of this. But now we're summing this up, and it's the exact same term for each of the n observations. So because of this sum, this is actually going to become n log sigma over 2. So that's where this term comes from. And then finally, we've just got the contributions that are coming from this exponential. So one of them is going to be 1/2 x, let's call it x1 minus mu sigma minus 1, x1 minus mu minus 1/2, x2 minus mu sigma minus 1, x2 minus mu, and so on. And you can just write that as simply as this term. So that's where this comes from. So it's just very simple. So the key point was just this independence assumption, which is in almost every case we're going to assume. And so then it's just a matter of just taking the logs and collecting terms, and that's what you end up with. Okay, so hopefully that was clear, and let me just zoom out. Okay, great. So hopefully now you just know where this term is coming from, and our aim is going to be to figure out what is mu and what is sigma. And because we're doing maximum likelihood means finding the maximum of this distribution with respect to mu and with respect to sigma. And sorry, and it's not a distribution, it's just a scalar value, of course. Scalar function. Okay, so let me erase all this stuff so it's a little bit clearer. Okay, good. Okay, so now the very first thing he says, and this is a really interesting point, and it's come up before. I think we had this earlier when we were looking at in the first chapter as well, when we were looking at maximum likelihood estimation for the scalar, when mu and sigma were scalars. So he said, by simple rearrangement, we see that the likelihood function depends on the data set only through the two quantities, this and this. And okay, so why does he say that? All he's saying is, well, if you just kind of rearrange these terms, you're going to see that you're interested in how the observations come in. Well, you're going to have a bunch of linear terms in the x's, and you're going to have some quadratic terms. And how do those linear and quadratic terms show up? So let's just do that. So we're going to get something like there's going to be a bunch of terms that are xn transpose sigma minus 1 xn. So there's going to be some of those showing up. That's going to be contributing here. So we're going to get a sum on n equals 1 to n. And then we're going to get, so that's gonna be related to this. And one thing to point out is that, well, it doesn't, how do we get xnt from this? And the way to do that, the way to realize this, and this is kind of an important thing to learn. So you can actually write this as this is going to equal to you can write this as the trace of xn. The trace of a scalar value is just that value. So, right? So I've just written the scalar value as the trace of itself. Like the trace of 2 is just 2. So 2 is, a scalar value is equal to its own trace. That's all I'm saying. Let's zoom in a bit more. Okay, so now traces have this really cool property, which is that that they have this kind of circular property. So what we can write is this is equal to, we can actually move this around. So you get, this is the trace of minus 1 xn transpose. Okay? And now the interesting thing is now traces are also linear. So now we can actually move this sum inside the trace. So now this is going to equal to the trace of sigma minus 1 sum on n equals 1 to n of xn transpose. Okay, so the quadratic term, the contribution of this quadratic term, of the quadratic terms here, this xn precision xn terms, you actually don't have to keep track of the individual xn. That's actually really useful. You don't have to keep track of the observations, every single observation. All you have to do is kind of keep track of this running sum here, and that will take care of at least this quadratic contribution. So that's one piece, and the other piece is just a linear component, and that's just going to be like the mu's multiplying by the precision and then multiplying by this term. So that's going to be sum of n equals 1 to n of xn minus mu transpose precision, and then forget the sign, there's going to be mu there, right? And again, we can so expand this out, and it's going to be something that doesn't depend on x times n xn transpose sum minus 1, quote, precision, sorry. And now you can just see, well, the term that's showing up is not the xn's individually, but actually you can just add them all up. So the linear component, what matters for the linear component is actually this running sum. You don't have to keep track of every single observation. And that's really useful, right? Imagine you have 10,000, 100,000 observations. You're processing videos, hours of video. Every single frame, you're going to have thousands of observations. Do you want to keep track of every single one? No, if you can avoid it. And so it looks like here in this situation, we can avoid it, because it turns out that at least for figuring out the maximum likelihood estimates of these parameters, all that shows up isn't, it's not the individual parameters showing up in complicated ways. It's just their sum, in one case, and this kind of outer product, the sum of the outer products in the other case. So that's very, very useful, and you should always be on the lookout for those situations. Okay, so yeah, so the likelihood function depends on the data set only through two quantities, this and this. So I've shown you how that happens. Now these are known as the sufficient statistics for the Gaussian distribution, and we'll see some more of that, I think, actually later on in this chapter when we talk about the exponential family. But just take that as a given for now. Okay, so using something in the appendix, which we'll talk about in the next video, the derivative of the log likelihood with respect to mu is given by this thing. Okay, because remember, the game is going to be maximizing this function, so we want to maximize the function, and then we want to take the derivative of the function and set it to 0. So when you do that, so we do that for mu, we set the derivative to 0, and then we get the solution, the maximum likelihood estimate, and it has this kind of really nice intuitive expression. It's just the mean of the observations. So it says, the maximum likelihood estimate of the mean of your Gaussian is just the mean of the observations. So kind of very intuitive. Okay, which is mean of the observed set of data points. So the maximization of 2 point, which is our log likelihood, sigma, is rather more involved. And this is what we're going to talk about in the next video. So the simplest approach is to ignore the symmetry constraint and show that the resulting solution is symmetric as required. So that's the approach that we will take. So I'll show you how to take derivatives of functions like that with respect to matrices, which is going to be which I have found extremely useful. Hopefully you will as well. So check out that video for how to actually compute the derivatives. But if you do and you set it to 0, you actually end up getting this expression, right? And it says, which involves mu ml, because this is the result of a joint maximization with respect to mu and sigma. So all he's saying is that you're going to, when you're going to take the derivative of this with respect to mu, set it to 0, take the derivative with respect to sigma and set it to 0, and you'll find that the expression for sigma involves that expression you found for mu. So you're actually finding the solution. You are finding the location in mu and sigma space where they're kind of jointly maximized. So the mu at that location is the maximum likelihood estimate, and the sigma is the for mu, and sigma is the maximum likelihood estimate for sigma. Okay, the result is expected and takes the form this. And why is it expected? Well, you can see that this is kind of like computing your kind of empirical covariance, right? So you're taking, just like you're taking your observations and subtracting from them their mean and taking the average of that. So this is kind of a, you're just doing, you're saying, look, my maximum likelihood estimate of the covariance is my empirical covariance, and maximum likelihood estimate of the mean is the empirical mean. Note that the solution for mu ml does not depend on sigma ml, and so we can first evaluate mu of ml and then use this to evaluate sigma ml. I think if there was some dependence, then you might have to do some iterative thing where like you first evaluate one, then the other one, and you keep going and you hope it converges. But here we have this nice situation where the maximum likelihood estimate of the mean doesn't depend on sigma, so you can just evaluate that and then plug it in here. Now that you've got these expressions, you want to kind of evaluate how good they are, and one measure of how good it is the measure of bias. So it says, on average, so over data sets, what is the average, what is your how does your maximum likelihood estimates, how do they relate to the true estimates? And if they're equal, then you say something is unbiased. And if they are different, then you say, well, the estimate, that estimator has a bias in it because on average, it doesn't actually equal to the population value. It equals some other value. And bias is, generally you want to reduce the bias as much as possible. But as we'll talk about later when we talk about the bias variance decomposition, sometimes it's okay to have a biased estimator because it'll allow you to reduce variance and etc. We'll talk about that when we get there. But either way, we find that, okay, so the maximum likelihood estimate is unbiased. So unbiased. But this one is actually biased, right? Because sigma, the expectation of this, the maximum likelihood estimate of the covariance doesn't actually equal to the true value, but it actually is something that will be close when you have thousands of parameters, when n is very large, but it's not exactly the same. So there is this bias there. So we see the expectation of the maximum likelihood estimate for the mean is equal to the true mean. However, the maximum likelihood estimate for the covariance has an expectation that is less than the true value, and hence it is biased. And there's actually, I think in the previous chapter, there was actually a very good explanation for why this was, and it was because the maximum, this expression that we're using, it's computing the mean of the data It's essentially it's thinking that the mean of your data is the true mean is actually the mean of the observations, and so that'll just kind of tend to shrink. It'll tend to shrink the covariance because the mean will be will land kind of in the middle of where your observations are, and doesn't quite account for the scatter that the true that the full population has. I think there's a we talked about this in an earlier video. I will put a link to it in the description, because I think there's actually a really good picture that Bishop puts that really expresses this idea. So it's a really interesting point of why this bias is there, and go have a look at that. But either way, so we've got this bias. So the question is, we want to get rid of it. So how do we do that? Well, we just modify our estimator. We just kind of rescale our estimator by putting this 1 over n minus 1 over it. And why does that fix things? Because we'll just check this out. So we can actually just write this as, this is going to equal to 1 over n times, all this, times n over n minus 1. Right? So that's all I've done is I've just written that in a different way. So now we say that if the expectation of this is just going to equal to the expectation of n over n minus 1 times 1 over n times all that junk. Well, expectations are linear, so this is just going to equal to n over n minus 1 times the expectation of 1 over n all that junk, and I've kept the 1 over n inside because, well, that was this sigma ml estimate up there, right? So this was going to equal to n over n minus 1 times the expectation of sigma ml, which is going to be n over n minus 1 times n minus 1 over n of sigma, and these things cancel out, and lo and behold, you get the sigma you were interested in. So it's just just a really simple and simple way to convert your estimate, your biased estimator, into an unbiased one. Another way you can, so that's just something kind of, you could have thought up. Another way to think about it is, from the statistics perspective, is that you want to divide your kind of, I guess, your sufficient statistic is kind of running sum by the degrees of freedom that you have in the data. And here, when this maximum likelihood estimate, we're kind of assuming we have n degrees of freedom, one for each observation. But actually, we've used up one of those degrees of freedom because we've computed this population mean from those observations. So in fact, we actually have n minus 1 degrees of freedom. There's actually n minus 1 degrees of freedom in this estimate. So to get an unbiased estimate, we should actually divide by the effect, the actual degrees of freedom, which is n minus 1. So you can kind of come at it from a statistical angle, and figure out what this factor should be to get an unbiased estimator. Cool. Okay, so I think that's all I wanted to talk about in this particular section. So we've just kind of stated these results. The general approach is very simple. You get the ln, you get the log likelihood of your parameters, and you just maximize that with respect to mu and sigma. We haven't talked about how to do that, how to actually do that maximization. I mean, the approach is always take the derivative and set it to 0. But how do you take those derivatives? So in the next video, I will actually show you how to compute derivatives of functions like this with respect to vectors and matrices, because I think it's very, very useful, and it's just something you should know because you'll use it all the time, because I know that I certainly do. So hopefully you'll tune in for that, and yeah, so thanks for hanging out, and I hope to see you in the next video.